learn about square root. So for a positive number, square root of x is denoted by this sign square root of x, or it's nothing but the same as x raised to the power of 1 by 2. So square root of x times square root of x is equal to x. So we've seen how x can be written as square root of x can be written as x raised to 1 by 2 times x raised to 1 by 2, and then we can add the two exponents, and then we get x. So square root of xy squared is same as xy. Note, square root of xy is not equal to square root of x plus y, as is in this example. Yeah. So we know how to deal with square roots. Like square root of 9 plus 16 is not same as square root of 9 plus square root of 16, which is 7, but it's actually same as square root of 25, which is 5. So knowing how to deal with these functions and equations is super important. If we want to now solve for a polynomial equation, for an example in microeconomics, a polynomial equation could look like, a general form could look like ax squared plus bx plus c equals 0. Or this could also be, let's say, your profit function. Let's say you're given profit function, profit as a function of quantity, q, and you want to maximize profits, and you want to solve for q. So similarly, we need to be able to understand how to solve for a polynomial equation. A general solution to this polynomial equation, meaning the value of x is equal to minus b plus or minus square root of b squared minus 4ac upon 2a. So there are two solutions, one with a plus and one with a minus. So being able to solve for this is important, because given profits, we can solve for maximizing where there is maximizing profits for a given value of q. Similarly, given an equation, we should be able to solve for x, or in this case, we are solving for q. So solving for polynomial equation, given a general equation like this, we should be able to solve for x. Yeah. So take an example, 2x squared minus 4x plus 1. Let's say we're trying to solve for x. Here we can substitute this minus b, so minus of minus 4, plus or minus square root of b squared minus 4 squared minus 4ac. A in this case is 2, remember, a is 2, c is 1, b is 4. So we get x to be 1 plus square root of 2 by 2, and x can also be 1 minus square root of 2 by 2. So this general form assumes b squared is greater than 4ac, because that's when you can take the square root. If b squared is equal to 4ac, then there's only one solution, right? So solving for polynomial equation will help us in future when we maximize profits and you want to solve for quantity, for example. Yeah. So solving for polynomial equations is one. And let's say we are given two lines. We should be able to plot lines in two different forms, the slope-intercept form, and we should be able to build a line in a general form as well, right? From when we're given two different data points, we should be able to build lines from them. So why is lines and knowing about lines important? Well, you could be given a function, demand function, that says QD equals 100 minus 5P, which is what is your demand for the goods that you're producing. So Q is a quantity demanded is a function of, the price, and then quantity supplied can also be another equation as a function of price. So given two equations, this is an equation of a line. So you should be able to plot a line that looks like this. In this case, m is the slope. Given a line y equals mx plus b, m would be the slope, b would be this intercept. Yeah. So positive slope is when this line looks like this. A negative slope would look like this. Looking from left to right, the line goes down. Looking from left to right, this line goes up. So that's a positive slope. So given slope and intercept, slope m, intercept b, we should be able to build a line that looks like this on an xy coordinate. Yeah. So given an equation of line, we should be able to solve and plot the line. Yeah. Given slope and intercept. And a general form of the same line can be written as ax plus by minus c equals 0, right? And you can rewrite this to be in the same form as y equals mx plus c. Yeah, and that is mx plus b, and that's same as what we have here. So in this case, m is minus a by b, and b, small b is capital C by capital B. Yeah, same as mx plus b here. So given a line, if we can draw this line, then we will know how is the line, is it upward sloping, downward sloping, and things like that. We should also be able to plot a line given two coordinates, x1, y1, x2, y2. So for example, if we are given a line that looks like, this say this is x1, y1, and x2, y2, these are the 2 points, we should be able to draw a line like this and form an equation of this line, right? So given x and y. So how do we do that? Well, if this same line needs to have and satisfy both x1, y1 and x2, y2, so what we do is substitute in the general slope intercept form, and we say, hey, y1 should be equal to mx1 plus b, and y2 should be equal to mx2 plus b. So in this case, the slope, given these 2 points, you can calculate the slope as y2 minus y1 divided by x2 minus x1. And you can also calculate the intercept b as x2 minus x2 y1 minus x1 y2 divided by x2 minus x1. Yeah, I've derived this, but in a sense, what you do is you assume both of these to be true. You subtract y2 minus y1, you get the slope. You substitute the slope in the second equation, you get the intercept as a function of these 2 points. So given 2 points, you should still be able to form a line because you can build the slope and you can build the intercept, and then you have y equals mx plus b. So this is super important because then you can draw the demand function, supply function, and all of that given 2 different data points, and given slope and given intercept. So that's the lines in 2 forms. If we are given a function that says a raised to x equals b, and we were asked to solve for x, how do we do that? Well, that's where logarithm comes in. If we're given a raised to x equals b, x is then equals to log of b divided by log of x. That's the solution. So let's see where we can use this, right? So if we are given, let's say, how long will some investments that we're making in a company take to break even? So you're trying to calculate time. You're trying to calculate, hey, what is the amount of value in future period of time for the principal that I pay, for the rate of interest that I'm paying, and how long will it take for me to break even, right? So given this, you want to calculate t. T is an exponent. So t can be calculated. So this is same as a raised to t equals b in some sense, right? X raised to, or maybe let's rename this to be a equals b raised to t in some form, right? Where a is a and b is p plus 1 plus r. So if we're given this, we should be able to solve for t by using this equation. So yeah, so let's see what log is. So a raised to x equals b, we can solve for x, and x is, in this case, would be log of b upon log of a. Yeah, so that's what we see here. And let's see how we derive this. In a sense, this requires, to understand log, we first need to understand exponents as a function. So e raised to x exponent, or exp of x, is basically a graph that looks like this. Yeah, it's a graph that looks like this. When x is negative infinity, y tends to go to 0, right? But when x tends to positive infinity, y tends to go to positive infinity, right? So in a sense, for every y greater than 0, this value is defined. So for any x minus infinity to plus infinity, y is always positive. And this e is derived to be equal to 2.71, approximately 2.718, right? It's the base for the natural logarithmic function. In a sense, it's modeling the exponential growth or increase in y as x becomes positive, right? As x increases, y grows exponentially. And for every y greater than equals 0, there exists x such that e raised to x equals y. Well, why is this important? We can map this, right? This is invertible in that sense that if you have x, you can get y, and if you have y, you can get x. So, so logarithmic function is an inverse of exponent. That's why we try to learn about exponent. So log of exponent of x is x. So if we understand exponents, we can understand logarithmic functions. Yeah, and exponents are when x tends to negative infinity, y tends to 0. When x tends to positive infinity, y tends to positive infinity. And that's the exponent function. Logarithmic function is the inverse of the exponent function. Yeah. So log of e raised to x is equal to log of y, right? And so x is equal to log of y. So in this case, if we're given this, we can solve for this. Okay, so log of x times, let's look at some of these properties of logarithm. So log of x times y is log of x plus log of y. Log of x divided by y is log of x minus log of y. Again, this can be derived through the exponent connection, meaning every x can be written as e raised to a unique number a. Y's can be written as e raised to a exponent raised to a unique number b. So now if we substitute x and y in this log function, we can write this as log of e raised to a times e raised to b, or log of e a plus b, or a plus b, where a plus b is same as log x plus log y. So log of x times y is log x plus log y. Log of x divided by y is log of x minus log of y. Log of x raised to some constant is constant times log of x. So now we know how we did this, right? So now if we're given a raised to x equals b, we take logs. So log of a raised to x equals log of b. X log a equals log b. And so x is equal to log b upon log a. So we are able to solve for any generic equation, or in this case, this equation, where we're trying to find out the exponent t. And we take logs, and we can easily get that and solve for that exponent. Okay, so that's logarithm. And now let's look at, if we're given an equation, a linear equation. If we're given a linear equation ax plus b equals c, then we can easily solve for x, because we can substitute, move all of the constant to the right hand side. So one equation with one unknown, we can easily solve it. Yeah. Similarly, if we have two equations, if we have two variables, then we need two equations with two unknowns. If we have three variables we need to find out, then we need three equations. So to solve for those three variables. So if we're given ax plus by, so x is a variable, y is another variable, then we need another equation, dx plus ey plus f equals 0. If we're given two equations with two unknowns, we can substitute away and eliminate from two equations to one equation. So meaning substitute y as a function of x in from second equation in the first equation, then we'll have one equation with one unknown x. Yeah, and we can solve for it. The other important part is differential calculus, where we're trying to find out the rate at which some things change. For example, you want to find out, hey, how is your cost going to increase as you increase the quantity of goods that you produce? The amount of production goes up. How is your cost going to go up? Yeah. The other part is integral calculus, where you're trying to find out the area under the curve, like, hey, how much is your customer willing to pay minus how much they actually paid. Hence the difference between those two areas is the area under the curve, consumer surplus, like how much did they enjoy as a surplus to them. So now let's understand differential calculus, which is trying to find out the rates of change of something. So rates of change of a function at x is defined as d by dx of fx. It's nothing but saying, hey, as h tends to 0, meaning there's between a very small interval, how is this function changing where h is tending to 0, f of x plus h minus f of x divided by h, meaning with very small sampling, when h tends to 0, what is the difference? What's the rate of change? F of x, rate of change of f of x at x can be written as f dash of x. It can also be written as dy by dx because y is a function of x. Or it can also be written as, for revenue functions, it can be written as marginal revenue. For cost functions, it's the same as marginal cost, which is nothing but rates of change of revenue, rates of change of cost. So when you're trying to find out like how is your costs increasing when you increase your production, or in this case, how is your profits increasing in this graph as you increase the number of items produced, you will see that here at this point it's peaking out, meaning the rates of change at this point is equal to 0, right? So rate here is equal to 0. Rate of change here is equal to 0. So that's your point where this is that item where you would want to probably stop. So this is where practically you can find out, hey, my profits are increasing, but beyond a certain point it's actually reducing. So if you want to find out how many items you should be producing, you would want to understand how to find out the differential. So f of x differentiated can also be written as dy by dx. It can also be written as df of x by dx. It's the same as f dash of x, or it can be same as marginal x, right? So in this specific example, if you want to find out max profits, you do df of x by dx equals 0. Yeah. So understanding how to find rates of change is important because then you can find out where is it peaking, as an example. Yeah. So there are 6 specific properties of derivatives that you need, actually 7, and that's all that you need to really master some of the things that are applicable in a microeconomics class and some assumptions that are needed for derivatives. The first one, if given a function f of x equals k, where k is a constant for all values of x, then f dash of x, which is dy by dx, or the derivative of f of x upon x, derivative of f of x by x, is same as f dash of x or marginal of x, right? Marginal of revenue and marginal cost is the only place where we use this marginal piece, but derivative of a constant is equal to 0. That's the first property, yeah? For f dash of x equals 0. Derivative of function f of x, it's given as, let's say, when now we are given function f of x is equal to alpha b of x plus beta g of x, where alpha and beta are constant, but b of x is a function of x and g of x is a function of x, then f dash of x, meaning derivative of a function, is alpha b dash of x beta g dash of x. So when a function is f of x is b of x times g of x, then derivative of f of x is b dash of x, meaning derivative of x times g of x, plus b of x times derivative of g of x, g dash of x, derivatives g dash x. Yep. So that's the product rule. This is the addition rule. Yeah. And then we have the chain rule. If function x is given as function of b times function of g of x, then derivative of f of x is equal to derivative of g of x times derivative of b of x times derivative of g of x. Yeah. Function, if it's given derivative of e of x, it can be written as e of x. Yeah, it's the same. Derivative of a log function, log of x, is 1 by x. Derivative of x raised to the power z is z x raised to z minus 1. Yeah, so if you're given a function f of x is x cubed, you want to find out f dash of x or derivative of x, it's 3x squared. Basically, you take the numerator in the front and then reduce it by 1. So x raised to 4 is 4, x raised to the 4 minus 1 is 3. So given e of x, derivative is e of x. Given log of x, the derivative is 1 by x. Given x raised to z, derivative is z x raised to z minus 1. So if we understand this, and then we understand the product rule and then the chain rule, the addition rule, and derivative of constants is equal 0, that's all that we need to understand and do this differentiation for the equation that we'll get in a typical introductory microeconomics class. Yeah, thanks.